we continue PPO. And today we will mainly study two things, GAE and TRPO. Actually, today we will not study PPO. From next class, we will study PPO, but today we will study some basic background of PPO. So first, let's start with the GAE. And this is from slide from the midterm exam, right? Remember this one? N-step estimator. At the end of policy gradient, we learned this kind of N-step estimator. So there were Monte Carlo and Bootstrap. And this N-step estimator is just a combination of Monte Carlo and Bootstrap. So the Monte Carlo, where is it? This is just the Monte Carlo, this one. This one is Monte Carlo. Entirely rely with the true reward. Let's say we have some rollout, let's say we have some trajectory, and then we can compute true reward, right? Without relying on neural network's output, we can compute true reward and entirely relying on such kind of true reward to get advantage value. That is Monte Carlo, right? And this is the bootstrap, so the very opposite thing. Instead of entirely relying on true reward from environment, we can use models output, our policy network's output, to get advantage. So this one has this is Monte Carlo, bootstrap, and this is true rewards of low bias, but high variance. This is it could be wrong because we rely on models output, so bias is high, but variance is low. So they have some different characteristics. So the motivation of N-step estimator is just combining these two things, combining Monte Carlo and bootstrap, so we can make some balance between bias and variance trade-off. That was the motivation of N-step estimator. And GAE actually start with this one, N-step estimator. And last time we also learned this one. We learned the problem of policy gradient, and one of them is how can we measure difference in terms of between policy. Let's say we have two different policy functions, and how can we measure distance between two policy functions? So mathematically, we derive this kind of thing, and it turns out that we can. So this is the difference of value of values from two different policy functions, right? We can define distance between two different policy functions. Let's say distance of values from each policy function, and then it turns out that we can rewrite this value difference with this one. At the beginning we only have the pi dash is where is it? Pi dash is a new one. New pi is old. Right? At the beginning, we have trajectory from new policy, but that is inefficient because every time we update, the motivation of this one was using, we'd like to change to off policy, right? Because in on policy, every time we have some data from new trajectory, we only use them once, right? So the on policy, off policy, use once, use data more than once. So on policy, let's say we have some data from trajectory and then we update our weight, right? We update weight of our policy function only once, and then we do not store such data. For example, we learned the replay buffer, right? We do not use replay buffer. In on policy, we do not use replay buffer. Just use that data only once and then just discard it. That is on policy. But as we learned, that is data inefficient, right? So the motivation of this kind of off policy learning is we'd like to reuse data. Let's say we have some data and then we already updated our weight of policy function, but we would like to use it again because it is data efficient, right? So So we'd like to transit from on policy to off policy for the data efficiency. And here, so that we have pi dash is a new policy after updating, and then pi is just an existing policy function. And the difference between this policy function, at the beginning, the trajectory was only from new policy function. That is data inefficient, and that is on policy, right? Every time we update our policy function, training data is always from new policy function. That is on policy. This is on policy, right? You understand? So the tau is trajectory, but every time we update pi, it becomes pi dash, and every time we update training data is from new policy function, so that it makes data inefficient, which could be seen as a on policy learning. But for the data efficiency, we like to transit from on policy to off policy, so that is the reason why we change the trajectory. Originally, the trajectory was from new policy, but we'd like to change trajectory from old policy. That means we can reuse data, right? So that is the motivation of this kind of off-policy learning. And to drive this kind of thing, to change tau is sample from new policy to action is sample from old policy, we introduce a important sampling trick. This is important sampling trick in statistics. We just multiply the ratio between the output of policy function, new policy function, divided by old policy function. That is called important sampling. And as I said, the primary goal is to enable data the primary goal is to enable data reuse through off-policy learning by numerically correcting the likelihood of an action as if it had been taken by the current policy, pi dash, rather than the old one. Right? That is consistent with this one, right? So we'd like to change to off policy, but originally the trajectory training data was from new policy, but we change it to old policy. That is called important sampling. And the motivation is just the data reuse, data efficiency. That is what we learned in previous class. So based on this one, based on n-step estimator, and what's this one? Important sampling, we'd like to transit to off policy. So the GAE is like we'd like to combine important sampling, but we'd like to improve this one. Let's say we have this one advantage, right? We'd like to improve the advantage. That is the motivation of GAE. GAE is where is it? GAE is a generalized generalized advantage estimation, right? It is relative advantage. In previous term, we have advantage here, right? So GAE is about this one. Important sampling is about the ratio between new policy and old policy. GAE is about this one, advantage. The role of important sampling, as I said, we'd like to transit to off-policy learning for the data, to reuse data, for the data efficiency, enable the reuse of trajectory collected by an old policy, I/O, to optimize the current policy, I data, weight correction, numerically adjust for the distribution shift using the probability ratio, right? This is consistent with this one, right? We introduce this additional term, ratio between new policy and old policy, to numerically adjust it for the distribution shift. That is the role of important sampling, but here, let's say a reliable signal, A. We have A here, right? Advantage. Even with perfect IS correction, the learning process will fail if the advantage estimate is noisy or inaccurate. And the traditional Monte Carlo estimate are unbiased but suffer from extreme variance, which is amplified and multiplied by the IS ratio. We learned that Monte Carlo suffer from high variance, right? It has low bias, but high variance. As we always use true reward from stochastically sampled actions from policy function. So we'd like to transit from previous n-step returns to GAE, right? So GAE, generalized advantage estimation, provides a sophisticated weight balance, bias, and variance by exponentially weighting various n-step returns. And by producing a clean and stable advantage signal, GAE mitigates the inherent instability of important sampling, making all policy updates like those in PPO robust and efficient. So that is the motivation of GAE, why we introduced GAE. Because to make a balance between variance and bias. And we will learn definition and what is GAE in later, but this is motivation of GAE. In particular, we'd like to stabilize the entire whole learning process. And although we introduced IS, the estimated advantage could still be very noisy and high variance. In particular, if we rely on MC or smaller n-step, then the variance could be very high, and that could make training very unstable. So we'd like to transit from n-step returns to GAE. And we learned n-step advantage estimator, right? These are just what we learned, n-step advantage estimators. So for example, if n equals to 1, then this is the n-step estimator's return, right? We only use true reward only once, right? True reward only once. The remaining things are just from model's output, right? If n equals 2, then we use true reward twice. And remaining things are model's output. If we use if we set n equals to infinity, then almost all, theoretically, all reward are from true reward, right? That is the n-step advantage estimator. And then we can define this one, delta, now sigma. Then we can get this one. We can rewrite this one, right? You can see this one. This is exactly the same as this definition of this one, right? So that we can rewrite like this one and then this one. But if n equals 2, then we can rewrite this one, right? And if we can generalize this one. For n-step advantage estimators, we can make a generalized expression like this. And here's definition of GAE. So these are from previous slide, and GAE is exponentially weighted average of k-step estimators. So as you can see, this is the lambda is a hyperparameter, and we have multiple n-step estimators returns, right? It's very interesting. So previous n-step estimator, once we set n equals to some scalar, then we only use that one. But GAE, it uses exponentially weighted average of k-step estimators. So there are multiple n steps. N equals to 1, n equals 2, n equals 3, n equals to 4, n equals to infinity. We use all these n-step estimators. We take them into account, right? And all these n-step estimators returns are exponentially weighted. And then we average them, that becomes GAE. So GAE is, as I said, GAE is not a single estimate. So previously, n-step estimator is just a single estimate. If we set n equals to 1 or 2 or anything, it is a single estimate. But GAE is not a single estimate. It's not a single estimate. It is a weighted average of all possible k-step advantage estimators. And it considers one-step view, two-step view, and all the way to infinite step view simultaneously. And this is a mathematical definition of GAE. And let's see what it exactly means. And here we have lambda, right? It's called decay factor, usually in the range of 0.95 to 0.99 range. Similar value with the gamma, right? Where is it? Gamma, discount factor. If lambda is very close to 1, what happens? What does this mean? The estimator converts the Monte Carlo return, utilizing actual returns from the entire trajectory to ensure an unbiased signal at the cost of high variance due to environmental noise. If lambda equals to 1, then we use all this one, right? For, let's say we have A at 10, then it has like a 10 true reward, right? If lambda equals to 1, we do not decay true reward for future time step, right? That is exactly the same as the Monte Carlo. So if lambda is very close to 1, of course this one becomes very smaller. But if lambda becomes 1, close to 1, then the GAE It's very close, becomes very close to Monte Carlo. What about the opposite thing? This is lambda equals to 1, lambda is close to 0. Then definitely opposite thing. The estimator becomes equivalent to one step temporal time difference, which is just bootstrapping, right? We only use true reward only once. Remaining things are entirely from model's output. So it's just a one-step temporal difference, relying heavily on the current value function to provide a low variance but potentially high bias update. And the term here, the term 1 minus lambda exponent k minus 1, this one. 1 minus lambda and lambda square, we have this one. Determines how much trust we place in each k-step estimator. For example, near terms, as lambda is a range of 0 to 1, near term receive higher weights, right? Definitely. Providing low variance signal based on immediate rewards. And long term receive lower weights, incorporating low bias information from the distant future. And so why we have this one? Why we have this one? It's just a normalizing constant. It is a normalizing constant based on the, we learned this one, right? So 1 minus lambda, 1 minus lambda here, 1 minus lambda square becomes 1, right? But we can rewrite lambda. We can rewrite this one as the 1 minus lambda sigma k equals to 0 to infinity lambda k, right? It's 1. So it's just a normalizing constant. So we are doing exponentially weighted average so that we'd like to make the coefficient for each n-step estimator. Summation of coefficient of all n-step estimator becomes 1. That is the reason why we have this one. And information fusion via TD errors. The second line shows this one. Second line shows that GA effectively smears the TD errors across time. It balances the reliability of current prediction V against the authenticity of actual reward by tuning the single hyperparameter lambda. Right? So as I said, if lambda is close to 1, we treat our GAE very close to MC. If lambda is very close to 0, then we treat MC, the GAE like a bootstrap. Usually, but this kind of range, very close to 1. GAE is, DQN, we learned DQN, right? DQN is not used these days. GAE, very widely used these days. And it is actually presented 10 years ago, iClear 2016. High dimensional continuous control using generalized advantage estimation. GA is exponentially weighted average of k-step estimator, and here, so until this one we learn, and then we can rewrite this one again, and we can simplify the GAE like this one. These are all included in paper. If you're interested, you can read the paper. And let's check your understanding. The definition of AK just the n-step estimator, and GAE like this one. Let's check your understanding. So what are properties of GAE gamma lambda equals to 0 and GAE gamma lambda equals to 0.99? Which are true? So for your reference, TD and return is the n-step return. So the first one, GAE R lambda equals to 0.99 is the advantage function using a TD0 return. Second, GAE. First one, let's check for first one. Anybody think first one is correct? Correct? No? Raise your hand if you think it's correct. If it is true, raise your hand. How about this one, B? GAE gamma 0 is the advantage function using TD0 return. This is true? Raise your hand if you think this is true. It's true? How about this one? The C, the bias of GAE gamma 0 is likely to be larger than GAE gamma lambda equals to 0.99. Is this true? Raise your hand if this is true. So majority of you guys think FTT. Let's check. GAE is advantage function using TD0 return. TD0 return is like an n-step return. But as I said, lambda equals to 0.99. Lambda is very close to 1. It's very similar to MC. So, but TD0 is very opposite of MC, right? Just a bootstrap. So this is false. GAE gamma 0 is the advantage function using a TD0 return. I think this is true. So GAE gamma 0 is like lambda is very close to lambda is 0. Then it's definitely true. Then the GAE becomes the TD0 return. The bias of GAE gamma 0 is likely to be larger than GAE lambda equals to 0.99. So this one is MC. This one is bootstrap, right? Bias of bootstrap is likely to be larger than the MC. This is true, right? So FTT. I think the answer is FTT. Bias of this one larger than this one. Okay. And how about this one? So what are properties of GAE gamma 0 and gamma 1? Select all. GAE gamma 1 is the advantage function using a TD0 return. Is it true? Anybody think this is true? No? Majority of the think this is false. And the second one, GAE gamma 0 is the advantage function using a TD0 return. Is it true? True? And variance of GAE gamma 0 is likely to be larger than GAE gamma 1. How about this one? False? True? True? Half and half. The bias of GAE gamma 0 is likely to be larger than GAE gamma 1. True? False? Not sure? True, raise your hand. False, raise your hand. Okay, 0.9, 0.1. Let's see. GAE gamma 1 is advantage function using TD0 return. This is the same as the previous question, right? This is false. And GAE gamma 0 advantage function, this is also same as the previous question. Variance of GAE gamma 0 likely to be larger than GAE gamma 1. GAE gamma 1, as I said, is bootstrap. And this is MC. Variance of bootstrap is likely larger than MC. This is false, right? Bootstrap has lower variance, right? So it is a lower variance than lambda equals to 1. This is false. Bias of GAE gamma 0 is larger than, this is BS, and this is MC. Bias of GAE gamma 0 is likely to be larger than MC. I think this is true, right? Bias of this one is larger than, bias of BS is larger than MC, right? Okay. So this is so far we studied GAE. And the background why we learned this one is from previous class slide, this one. We measure distance between two policy functions as a distance, a difference in value function. By definition, the policy gradient is on policy algorithm. So all the trajectory was from updated policy function, but that makes training very inefficient, data inefficient, because we cannot reuse all data. We always need to generate data. It's very data inefficient. We cannot collect large-scale data, right? So we'd like to change the trajectory to the old policy's trajectory by changing. We gradually change it, right? At the beginning, we change the action, and later we change the state by making some approximation. And here we introduce importance sampling to make the off policy, to move from on policy to off policy. And this is importance sampling, but despite we introduced this important sampling, the advantage function, it still needs to be accurate and lower variance. But n-step estimator is good, but GAE is kind of considering all these n-step estimator, exponentially weighting all the n-step estimator. That is the motivation of GAE, to make the advantage more reliable and stable and accurate, right? That is the motivation of GAE. And TRPO. TRPO, let's see this one, policy optimization. So issues with gradient step size. So what we are doing is summarized in this slide. What we want to do is just, let's say this is policy function, pi. What we want to do is just making policy function that can maximize this one. And we'd like to figure out the weight of policy function theta, right? And of course, the weight could be updated with this gradient descent or gradient ascent parameter update equation. And the gradient, how can we get gradient? That was tricky, right? In policy gradient, we'd like to train policy function by maximizing value. So there was no connection between policy and value function, but policy gradient theorem, we learned this in midterm, right? Policy gradient theorem said that we can define this gradient, and mathematically it is equivalent to maximizing value, so that we can use this gradient. This gradient is for policy gradient theorem. And still we have issues. The gradient estimate, these are issues. So far we learned this one, but still we have issues. The gradient estimate is only first order approximation. The function assumed to be linear, curvature information is not captured. Globally estimating the gradient can have high variance with large state and action spaces. Step size, alpha, this one, step size, is relative to the parameter and not objective function nor the policy. A larger step size results in overshooting, small step size results in slow performance. All these issues are applicable to just a usual neural network, just a neural network with supervised learning. All these issues are applicable, but these issues becomes in particularly important in reinforcement learning because we do not have large-scale data in advance. That is the difference between RL and supervised learning. In supervised learning, we have large-scale good data, good quality of data, so that although there is something bad happen, we can fix them, we can correct them with training from next batch. But here in RL, we do not have large-scale data in advance, so that this kind of issues could be, especially becomes important. So we'd like to address these issues. And this is motivation of TRPO, TRPO, Trust Vision Policy Optimization. That is the TRPO, Trust Vision applied to policy optimization. Policy optimization is what we want to do, right? We always want to optimize policy function. After a deep Q network, we change it to policy function, and our goal is always optimizing policy function. But some special thing of TRPO is the trust region, introducing trust region. Define a local trust region to be a region we think we understand better. Find the optimal point within this region, right? Actually, in previous class, we studied somewhat similar things in previous class. Let's say this one first. TRPO, Trust Region Policy Optimization, TRPO. Iterative policy gradient algorithm that ensures monotonic performance improvement by constraining the policy update to a trust region defined by a maximum K divergence between old and new policy. Do you remember this one? We have, in previous class, we studied this kind of relative performance bound, which is defined with the K divergence between old and new policy. Let's see the characteristics of TRPO first. Constraint-based optimization. TRPO treats policy update as a constraint optimization problem, ensuring the new policy stays with a small K divergence trust region from the old one to maintain the validity of the performance approximation. And so here, the important thing is that small K divergence. We will learn this later. Actually, we already learned this in previous class. Adaptive step size and second order. By utilizing Fisher information matrix, second order derivative, TRP automatically determines maximum possible step size. It automatically figure out maximum possible step size parameter space that satisfy the policy space constraint. And theoretical guarantee. The approach provides a monotonic improvement guarantee, solving the step size issue where a slightly too large update could lead to a catastrophic collapse in performance. Remember this slide? This is from previous lecture. And they're actually this one, relative performance bound, relative policy performance bound. We already learned this. So after changing action to the action is sampled from all the policy by introducing importance sampling, we still need to change state. Needs to be also sampled from all the policy. How we achieve this is making approximation. Let's say D, we learned the definition of D could be from previous lecture slide. Anyway, what if we can approximate pi dash and pi almost the same? Then we can sample state from D pi. That is the approximation that we made in previous class. For this one, to make this approximation work, make sense, we need to introduce this one. The difference between the value of two policy function could be bounded by this one, bounded by K divergence. This is the relative policy performance bound that we learned in previous lecture, and we actually skip this. How to set C, we will learn next time. That was included in previous lecture, and this time we will see how can we set C. So there are many things, but we actually already learned this. We are actually, in this slide, we actually learned all things about TRPO. TRPO introduces an iterative procedure for optimizing policies with guaranteed monotonic improvement. And here, monotonic improvement are due to relative performance bound, previous slide, right? Because here, the difference between updated policy and old policy, lower bound is already decided, right? We already have lower bound. That means we can theoretically say that we can achieve monotonic improvement. After updating, the updated policy is always better than previous one. That is monotonic improvement due to the relative performance bound. And first, the author proved that minimizing surrogate object function guarantee policy improvement with non-trivial step size. We already learned this one, surrogate objective function, right? By introducing importance sampling, right? Author's numerical approximation to ill practical algorithm, namely TRPO. All these equations are actually included in previous slide. We introduced this one with the importance sampling and making approximation, and monotonic improvement is due to the relative performance bound, which is in previous slides, that lower bound between two different values from two different policy functions is already given. Lower bound is given. And this is also from previous slide. So now we have tau is always from old policy, and the loss function. This is surrogate loss function. Surrogate means alternative. We want something, but we cannot achieve that. Instead, we do something. That is alternative and surrogate. Anyway, we already introduced this one. This surrogate loss function, right? In previous slide. And that becomes surrogate loss function in this slide, right? And the assumption of this surrogate objective function or anything that we are saying now is that two policy functions are similar, and mathematically they need to satisfy this one. That is relative performance bound, right? The TRP uses the same surrogate object function that we learned in previous class, derived from the performance difference lemma. This objective allows that we use the trajectory sample from old policy by importance sampling, and the constraint is where K divergence comes in. The approximation is only valid when the new and old policies are close. TRPO explicitly enforces this by adding k-divergence constraint, creating a trust region for a safe update, right? By assuming this one, by making constraint, k-divergence constraint, so TRPO, trust region, some region where the policy functions are close, where the closeness is defined with the k-divergence. That is the constraint that we need to apply when introducing TRPO. And here we have optimization. I mean, at the beginning of TRPO, we learned this one. Okay, we learned this one, right? Now we know what this means. The relative performance bound said that to satisfy relative performance bound, we need to make the two policy functions are close with the small k divergence. That is about the small k divergence. And the maximum possible step size second order derivative is about this one. Second order derivative up here. To solve the constraint problem, TRPO performs a second order Taylor expansion of the k divergence. This produces a Fisher information matrix which represents curvature of the policy space. And by using this matrix, TRPO computes natural policy gradient, which automatically determines the optimal step size maximum improvement without violating trust region. That is the important thing. There are many difficult things I know. There are Fisher information matrix, natural policy gradient. You do not have to study deeply about this one. Just you can get familiar with this. We can use Fisher information matrix to perform some second order derivative, and there is some natural policy gradient, but it allows us to automatically determine the optimal step size to maximize improvement without violating trust region. The important thing is that, so here, vanilla policy gradient, first order, takes steps in parameter space with the predefined learning rate, alpha. Here we have learning rate. Where is learning rate? Learning rate. Here, alpha. The previous PG, vanilla PG, original policy gradient, used alpha as a scalar constant. But with the second order derivative, our TRPO can automatically figure out optimal or maximal step size that do not violate trust region. That is the good thing of TRPO. And this mathematical rigor provides monotonic improvement guarantee, preventing the performance collapse often seen with a fixed learning rate. Fixed learning rate, original PG. And TRPO, with the second order derivative, it automatically figures out maximal step size that does not violate the trust region assumption. So let's see the difference between original PG, holistic gradient, and TRPO. Update space. Vanilla PG, parameter space, update weights directly without knowing how much the actual probability changes. That is actually what we learned in previous class, the problems of PG. The distance between parameter space and policy space is very different. And then TRPO, policy space, update space and policy space. Update weights while strictly controlling the change in actual probability distribution, which are mainly due to k divergence constraint and second order derivative. And step size. Vanilla PG, manual and fixed. Use a preset learning rate, too large causes performance collapsive, small is too slow. But TRPO, automatic adaptive, use second order derivative, Fisher information to find mathematically largest safe step. Data efficiency. Vanilla PG on policy, as I said. It cannot be used data. Discard data after a single gradient step. But TRPO, thanks to the importance sampling and the relative performance bound assumption, we now shift to off policy by importance sampling. We use data for multiple steps within a stable trust region. And finally, guarantee. Vanilla PG, no stability guarantee. TRPO, monotonic improvement because we have relative performance bound. Mathematical guarantee policy only gets better, never worse. Of course, in theory. So this is the difference between original PG and TRPO. Is okay? So TRPO is good, but as we always did, we learn something, there's some problem, we learn new something. TRPO actually has some problem, so that becomes the motivation of PPO. PPO is just theoretically almost the same as TRPO, but second order derivative is too expensive. Where is it? Second order derivative. It's too expensive. It takes too long time in practice. So PPO do very simple trick to bypass the second order derivative, to introduce some very mathematical trick, so that all this theoretically almost the same, with the TRPO and PPO almost the same, but PPO avoids second order derivative, which is too expensive. And PPO is very standard algorithm, and our final project will be based on PPO. Any question about